All right, hi everybody. I'm Gan, and this is Ryan. Yeah, we're going to talk about a little tool that we built called Fiano, and it's written in Go, hence the title. And so before we begin, many thanks to Ron Minnick, Julian, Andrea Barbero, and from various companies. And a lot of these, we took a lot of references from UEFI tool and UEFI firmware parser, which, as you may know, are already written in C and Python. And this is sort of an implementation in Go, but we have our own little take on it, particularly because we wanted it to be more scriptable and easier to use from the command line. Right. So I'll let Ryan go through the background.
All right. So I'll talk about a bit of the motivation behind Fiano. So in a pursuit of Linux boot, we found that we often encountered firmware images which we do not have the source to. So when we get the machine, we read the image, and we just have a large blob. And typically, for UEFI is very modular. It contains files. It contains a file system. And you'd expect to be able to, for example, mount it in Linux and see the files within it. But this isn't the case, and there aren't many tools for doing that. So we made this tool over the course of about 6 months. We got inspiration from other tools, such as UEFI tool. And it's fairly successful, and we've thought of many applications in which it can be used. So the primary one is for Linux boot as a build system. Another one is removing unnecessary dixies. So a dixie is a driver within UEFI. Oftentimes, UEFI firmware contains lots of unnecessary drivers, things that you don't want, things that no one really knows what they are. Oftentimes, you just want to remove them to decrease the attack surface of firmware. Another thing we're thinking about of using Fiano for is security forensics. So you could analyze firmware images, see patterns, and see if you could find issues inside of it. So I'll talk a bit about what Linux boot is for those who don't know. So the idea behind Linux boot is you take the Linux kernel and you add it to the firmware of the as a UEFI application. So currently we have it's quite successful. We have netboot, pixie boot. It replaces a lot of the functionality that existing UEFI images do. You should see Chris's talk at 3 p.m. in this room if you want to know more. So the way the UTK tool. So UTK is one of the primary tools within Fiano. There's a couple other tools within the Fiano toolset, but UTK mostly overshadows them all. So oftentimes you use these two names interchangeably. So we have, so this is often the workflow you'd go through for a Linux boot. So you take a firmware image off of your machine, either use flash ROM, a DediProg programmer to rip it off, or you use, you can actually build your own images with Tiano Core. You take a pre-built image, you have the binary file on your machine, and you run this command, UTK old BIOS, and then replace a shell with Linux. And then you save it as the Linux boot BIOS. And on some machines that we've worked with, this is enough to actually have Linux boot on the machine. It's like that easy, just one command. So yeah, so the two inputs to UTK is the original firmware image, Linux, and the output is a Linux boot BIOS. So then once you have Linux boot on in the firmware, you can start removing unnecessary drivers. So oftentimes, these drivers are made redundant by Linux. For example, you could immediately remove the whole USB stack. It's already in Linux. You can remove the net stack. It's in Linux. So we developed this tool called Dixie Cleaner to help you do that. Essentially, what it does is inside of UTK, it iterates through each driver. Some machines we've seen have 400 drivers inside of UEFI. And it goes through them one by one, and it tries to delete it. And then it runs a script, a test, like a shell script, which flashes that image onto the machine, sees if it boots. If it does, then it says we can remove that driver. If it doesn't, that means that driver is sort of load-bearing, and we could look into it manually, or maybe like another round, maybe another driver had a dependency on it. So I could give you a demo of this tool. So let's see here. Actually, this is a recording. So you see here in this folder, we have this test script. So essentially, this test script runs the OVMF image inside of QEMU. I just do that because it's fast. And then when we run UTK with the Dixie cleaner, what it does is it takes the OVMF image, tries to delete a Dixie, then it runs it through QEMU. If the Dixie can be deleted, if the driver can be deleted, then it leaves it off. If the driver can't be deleted, then it keeps it. So for example, this driver with this GUID, the tool deleted the driver. It successfully booted in UTK. Sorry, in QEMU, so we leave it removed. This GUID here, when we remove the driver, it failed to boot in QEMU, so we consider that driver load-bearing, and we leave it in the image. So after you run this for like an hour, it goes through all the drivers, and at the end you know which drivers you need, which ones you don't. Obviously, just booting the image isn't enough. So we set up a more thorough test, which checks to make sure, for example, we're able to access the network and lots of other functionalities, like all the memory's up, all the devices are there. And then this is a quick way. It's not quick, it takes about a weekend to run, but it's an automated way of figuring out which drivers are made redundant by Linux and which ones could be safely removed. All right. So I'll talk a bit about the internals of what a UEFI image looks like. So over the last 6 months, we really learned it's a bit confusing at first. So a firmware image contains a number of firmware volumes. So typically, the PEI would be in its own firmware volume. The Dixies would be in its own firmware volume. Oftentimes, there's another firmware volume, for example, for NVRAM. Each firmware volume contains multiple files, and each file contains multiple sections. So for example, a section might be the name of the file, another section might be the version, another section might be the actual contents of the file. But to make things very complicated, the way compression works inside of UEFI is you can't compress a firmware volume directly with LZMA. You have to compress a file. So to compress a lot of files at once, they put a firmware volume inside of a section of a file, and then they compress the section so that all the files in that firmware volume are compressed. So this took a lot of work to be able to parse correctly in our tool. But we're quite proud of the way we've organized our code to be able to parse it, and it's very easy to extend. So I'll give this back to Gon.
Right, so what else can UTK do besides the very fancy Dixie cleaner that we saw earlier? And the first thing, obviously, the most important is what is in this image, right? So you want to poke around, you want to see what files are actually on this system. Next, you want to be able to take them out. You want to extract and take a look at the individual files that are in the system. And then lastly is sometimes you want to change things, right? You know, modify certain, let's say the shell in the OVMF EDK image for the QEMU. You want to say, I want to replace that with a different shell, or I want to replace that with Linux, right? And then you save it to a new BIOS image. So let's start with the first one. So this looks like a lot of stuff. I'm going to go through it. But basically, you say UTK BIOS image and table, right? And we pipe it to less, but you could pipe it to any file that you wanted. And it shows you, first you have a couple of firmware volumes. In OVMF, the PEI is arranged at the top for some reason. And you can see the different files. And as Ryan talked about here, this is the nested firmware volume image. The GUID defined here is the compressed section. Here we just use any old LZMA compressor that you can find on your system, right? But here, and you can see a small listing of some things, right? Here is here's the name of the section or the file in general. So this is how you take a rough overall glance at what are all the things on my system. Then you have more commands for poking around. You can find specific files or specific dixies. For example, you can do a find by a string, a regular expression. You can say search for anything that has shell inside it. Or you can say, I have this GUID, find me the DXE that uses that file GUID. If you want to look at actual files, you can say dump and give it the same regular expression or GUID and a binary name, and you can dump the whole binary to another file for you to sort of look at, or you could do analysis on it. And we have count, right? So you can see how many dixies do I have on my system, how many PI modules do I have, how many SMM modules do I have on my system. Count will give you a rough idea of all of those things. So we know what we have. Let's actually modify some things. You can say remove certain dixies. Again, as you notice, we take GUIDs, we take regular expressions, and this is the same for a lot of our commands. So remove also takes the same format as find does. And you can say, after you remove all those things, save to a new image. It could be an FFS, it could be a dixie, it could be PEI, it could even be an SMM module, right? Doesn't really matter. And this is the one that we use more or less the most frequently. Replace the P32 section, right? You can say, I have this application, I want to change out the code segment of it. So I say UTK, the BIOS image. I replace the P32 section, which is the code section, of this particular thing called shell, with our own BZ image in the case of Linux boot. And you can say we can save it to a new image. So a lot of our examples here have talked about replacing with a Linux kernel, and more specifically because we use it for Linux boot. This doesn't necessarily have to be the case, right? You could potentially imagine like, I've compiled a separate EFI shell separately, and I want to replace that, right? It doesn't have to be just for using for Linux. The thing is, though, we can actually chain a lot of commands together. It doesn't have to be one by one. So you can say UTK, ROM image, and I want to remove a whole bunch of different things and replace the shell at the same time, and then save to a new image, right? So we have the ability to do multiple things in once, which makes it a lot easier for scripting. And this was one of our pain points with UEFI tool, which through the GUI was very hard to automate certain things. And so we simply took all the knowledge from there and tried to do it in a command line friendly interface. So if you don't take away anything else from the talk, this is an easily scriptable UEFI imaging editing tool. It's written in Go. It avoids rebuilding entire UEFI images. For speed reasons, we found it much quicker to replace certain components rather than to rebuild the whole image, especially, for example, with OVMF. And sometimes you just don't have the source, right? You want to look at certain things, you don't have the source. So this is one way you can do it. And we have the new automated DXE removal, which we found pretty useful on some systems. So this is on GitHub. It's all publicly available. We hope for more contributors. And even if you don't have time to contribute, use it and let us know if you have any pain points, like file issues, all that. All right. Thank you.
And the stickers are right over there.
So any questions?
I understood the tooling regarding trying to remove some DXEs and testing against the QEMU. How do you do that for a real system that may not boot at all if it's failed?
Okay, so for a real system, one of the techniques we use is we connect a flash emulator to the system, and then there's a timeout of about like 10 minutes or so. If the system doesn't come up in 10 minutes, we assume that Dixie was load bearing and we leave it in, and then we just emulate another flash part later.
Okay.
And the
So we use QEMU as the example. It doesn't have to be. Basically, whatever shell script you pass in at the end, if the shell script returns with a non-zero exit code, it means a failure. And if it's a zero exit code, it means success. So you can potentially have the shell script do all the work of flashing a new image onto an actual system, running whatever tests you want, and then coming back. Or it's up to you, basically. We provide the automated process of iterating through the files one by one, and then based on success or failure, adding it back or not. Think of it like a git bisect, if you've used something similar in that vein, right? It's a tool to help you iterate through.
So we have seen a problem where a vendor-provided UEFI image doesn't handle PCIe enumeration correctly. So sometimes it hangs. So can I use this UTK tool to fix that problem?
If you have your own solution with a binary that fixes that PCI enumeration, potentially, right? Or if you can make Linux do it the right way, again, this might solve your problems. We haven't really dealt with that specifics. This is really just about iterating through the UEFI file system and modifying things. But potentially you could use this to change some things if you wanted to. But that's on your own image, your own binary.
Okay, so firstly, I need to have that fix.
Yes, we can't. Yeah, we won't.
And
provide.
then replace that.
Yes. Yeah.
Okay, thank you.
Mm-hmm.
So does a tool interpret the dependency rule in UEFI image?
So the dependency sections in the UEFI image, we do parse them. We don't do much more with them at the moment. We do. There may be work in the future. We look forward to contributions on how to manipulate that dependency sections. Mm-hmm. But right now, I don't think we do that much with it. Yeah, Ryan, you can correct me.
Oh, yeah. Yeah, so actually determining the dependencies statically, like without running the code, is a very challenging problem because the dependency sections contain the protocol, like the GUID of the protocol, and not the GUID of the driver. So driver is registered protocols, which you only know at runtime. So it's almost impossible to determine that at like statically with the tool. Which makes it very challenging. We're thinking of like some ways, but nothing is really perfect because a lot of those dependencies all worked out at runtime.
Thank you.
One more question. So what about secure boot and tamper-proof systems? So if you make a new image, the signature changes, right?
Yep.
Okay, I'll take this. So yeah, boot guard is a problem. I assume that's what you're referring to. When you modify the BIOS image, boot guard. Yeah, so boot guard is a problem in more ways than one beyond this, right? So it would definitely make this impossible, basically. And for other reasons beyond this tool, we don't really recommend boot guard. Only for like maintenance and resale reasons. But beyond that, yeah, you're right in that if you have boot guard enabled on your system, you will not be able to change the image. That is true. Right? It has to be signed by your basically whoever signed the original image, right? Whoever your manufacturer, whichever your manufacturer is.
Okay, thank you.
Any more questions? Yeah. Yeah, we have time, so yeah. All right, thank you for coming.